Hi, welcome back to the Little Bang Discovery Club. I'm Wendy from Children's Discovery in Sydney, and this is session 4, which is all about a science fair. We'll get to that in a moment. Just a reminder that the children are the junior discoverers doing the thinking, and the grown-ups are their lab assistants helping them. And once again, probably be a good idea to pause the recording after I show you how to set up the experiment and then to go and try it. So what is a science fair? Scientists usually let other scientists know about their discoveries at a science fair, where they all get together and talk about what they've just discovered, or they might publish their work in a journal. Now, if this was a face-to-face Little Bangs like normal, you would have all tried an experiment through the week and then you would tell us about it today. But this is not a normal Little Bangs, so we can't actually have our science fair the way scientists do. But perhaps you've got friends that you might phone and talk about some of the science experiments that you've done, a bit like a science fair. Now, we're going to have a look at what happened in the experiments I showed you last time. So here I've got my little magnet on the back of my fish, and if I'm going to test what it will stick to and what it won't stick to. So I've got some things made of different things here. I've got a ruler made of wood, and I'm going to make a prediction that it won't stick. So if I try and put it on, no, it doesn't stick. So I got an expected result. I've got a chopstick made of plastic, and I'm going to predict that it won't stick. Try putting it on. No, it doesn't stick. I got an expected result. Now I've got a spoon made of metal, and I think that magnets stick to metal, so I'm going to predict that this time it will stick. And if I put it on, yes, it does stick. So I got an expected result. Now, what about this metal can? Metal, magnets like metal, let's see. I'm going to predict that it will stick. No, it doesn't stick. So magnets don't stick to every metal. This is an aluminium can, and magnets don't stick to that. But my spoon that it did stick to has got iron in it, and that's one of the metals that magnets stick to. So if you had your magnet sticking to things around your place, it's probably because they've got iron in them. So that's our magnet experiment. Now, our musical coat hanger experiment. I hope the grown-ups tried this one as well. Adam, could you please help me with this? We're going to get Adam back to hang the coat hanger from his fingers.
Am I going to get the loud gong again?
I hope so.
Right.
So when we tap the coat hanger, just a light sound to us, but when Adam puts it in his ears, he gets a, how would you describe it, Adam?
Like being underneath a giant bell.
Okay, so a huge, big sound.
Huge, big sound.
So what's making the difference? What's been different to how the sound is getting to my ears, which is where I hear sound, to how the sound is getting to Adam's ears?
You know, Wendy, my fingers, I can feel something in my fingers when you hit the coat hanger.
Can you?
I feel my fingers wiggling.
Your fingers are wiggling. Do you know what the special word is for that? When we hit something and it starts to wiggle or move backwards and forwards, do you know what that word is?
That'd be a vibration.
That would be a vibration. So when we strike the coat hanger, it starts to vibrate or move backwards and forwards. Now, how does the sound get to my ears when I'm not holding the strings, or to Adam's ears when his fingers aren't in his ears? What happens is the coat hanger vibrates and hits the air next to it, because the room is full of air, even though we can't see it. Hits the air next to it, which vibrates, hits the air next to it, which vibrates, hits the air next to it, which vibrates, and finally gets into my ear to my eardrum, which vibrates. But you can imagine the vibration, it's happening all around the room, so that the vibration is spreading out, so the bit that gets to my ear is quite small. But when Adam's got his fingers in his ears, and we make the coat hanger vibrate, it makes the string vibrate, which makes his fingers vibrate, so that the sound is actually getting to his ears along something much more solid than air, and therefore it's a much louder sound, much more resonant.
Awesome.
Thank you, Adam. Now, with our salt water and our tap water, I'm thinking that you might have got an unexpected result here. So just make sure our salt water is salty enough. When I put the egg in the tap water, it sinks. But when I put the egg in the salty water, it floats. Now let's try that with the grape. Grape in the tap water sinks. Now if you didn't do a grape, what do you think it's going to do in the salty water? Tell your grown up, what do you think the grape's going to do? When we put it in the salty water, it floats. Now why is the difference here? What's going on? So this one has just got water in it. This one's got quite a bit of salt in it. So the salty water is much more buoyant than the tap water. So that's why the egg would sink in this one and float in this one. Now this is an experiment that you can try for yourself. If you ever go swimming at a swimming pool that's got chlorinated water, you're going to be swimming in water like this, and it's more difficult to float than if you go down to a rock pool where the water is salty and it's more buoyant, so it pushes you up more and it's easier to float in salty water. And there are some places on Earth where the water is so salty that you can't help but float. So the example, of course, is the Dead Sea that's between Israel and Jordan. Now, there's an old test for how fresh eggs are. Mostly these days we buy our eggs from the supermarket and it has a use by date on them. But long ago, when people used to keep their own chooks, they used to get their eggs, and if they put it in the fresh water and it sank, they knew the egg was good. But if they put it in the tap water and it floated like it just did in the salt water, they knew the egg was not good. Because when eggs start to go bad, they make a gas inside them, and that makes them more buoyant. So if you ever put an egg into tap water and it floats, you don't want to open it because it's going to be very smelly. It's going to smell really bad. All right, now let's try our last experiment, which was sink and float with our pieces of blue tack. So we've got our 3 cups with water and we've got our 3 blue tack shapes. So our first spiral or round shape, what did you expect it to do? Sink or float. And then when you put it in, it sank. Our next shape, the flat shape, what did you expect it to do? Sink or float. And when we put it in, it sank. It's got stuck on my cup there, but if I let it, it'll go all the way to the bottom. What about our boat or our cup shape? What do you think it's going to do? Sink or float? Now, if we put it in very carefully without getting any water in it, we can get it to float. So the same strip of blue tack, you might remember, the same amount of blue tack, but made into different shapes, will determine whether it sinks or floats. So the shape was what was important. And that is why boats that are that sort of a shape, but are made from very heavy materials like iron and steel, will actually float even though they're so heavy. If they were a different shape, they wouldn't float. But then if you get water in your boat, then it will float. When it's filled up with water and no longer filled up with air, it will sink. Okay, so now I'm going to show you some new experiments to try this week. Now we're ready for our new experiments. The first one is called Disappearing Pencil, and I've got a puzzle that we're going to have a look at up close in a moment, where we count how many blue and how many red pencils there are, and then we swap the places of the bottom pieces of the puzzle and count again. So here we have our disappearing pencil puzzle. Let's count how many red pencils we've got at the moment. 1, 2, 3, 4, 5, 6, 7 red pencils, and blue ones we've got 1, 2, 3, 4, 5, 6. So can you remember that? 7 red pencils and 6 blue ones. Now I'm going to swap the puzzle pieces over. Now let's count again. Red ones first. We had 7 last time. 1, 2, 3, 4, 5, 6. One of our red pencils seems to have disappeared. And we had 6 blue ones last time. 1, 2, 3, 4, 5, 6, 7. So one of our pencils has changed colour from red to blue. Now, can you work out what's going on? Have a talk with your grown-up and see if you can work out how the pencils have changed colour. Now, our next experiment is about magnifying. And for this one, you need a glass with water in it and a picture from a newspaper or a magazine. And what you're going to do is hold the glass with water in front of your picture and see what happens to the picture. Now, depending on where your glass is, the picture might get bigger and it might even reverse. See if you can get it to do that. And then do the same thing with your finger. So your fingertip, put that near the water that's going to magnify it, and see if you can make your fingertip so big that you can see the little lines that are on there. And that's called your fingerprint. And then have a look at your grown-up's fingerprint. You should find that it's different to yours. Everyone has a different fingerprint. And can you also get your finger to reverse, to be, looks like it's coming from this way when it's really this way? See what you can do by magnifying with a glass with water in it. Now, our next experiment is called kissing balloons. So for this one, you'll need a couple of balloons blown up to the same size and 2 pieces of string about 30 centimetres long. And you're going to tie the string around the top of the blown up balloon. So a bit like our musical coat hanger, you can hang the balloons by their strings. So when you've tied them on, you're going to put them in front of your face about 5 centimetres apart, and then you're going to try and blow them apart. So while they're in front of your face, you're going to blow hard to blow them apart. Now, I'm not actually going to do it just at the moment because I want you to try it first and see what happens. Sounds pretty easy, doesn't it? Blowing balloons apart. See if you can manage to do it. Now, our last experiment is called raw or boiled, and this is where you need your raw egg and your boiled egg. Now, hopefully your grown-up knows that you've got a raw egg and a boiled egg, but hopefully the children don't know which one is which. So on one of the eggs, put the number 1, and one of the eggs, put the number 2, and you're going to try and guess which one is raw and which one is boiled, but without breaking the shells. So it would be easy to crack them open and see, but we're not going to do that. So you might look at them. They look pretty similar. You might give them a shake and have a listen. Can you hear a difference? You might smell. Will the boiled one smell more eggy, perhaps? You might try putting them in some water like we did last week, except this time it's just tap water. We haven't got any salt in it. Will it make a difference if it's raw or if it's boiled, whether it floats or not? Now, what did it do last week in the fresh water? You might remember that the egg sank, and that was a boiled egg. So you'd expect the boiled egg to sink again this time, but will the fresh egg, the raw egg, sink this time? Is there any other way to tell apart from cracking the shells? See if you can work out which one is your raw and which one is your boiled egg. So did you find out a reason that the pencils change colour? If you have a look, there are two pencils here that can be either colour. One of them is the lead, that's just the lead, and one of them there is just the eraser. Now at the moment, those two pencils are coloured blue. But when we swap them over, what colour do you think they're going to be now? Have a guess with your grown-up. So here's our lead only pencil and it's red. And here's our eraser only pencil and it's also red. So this is a clever picture that it's not an optical illusion, it's a clever picture that allows it to appear that the colours are, the pencils are changing colour. How did you go with your glass of water and your picture? Did you get it to get much bigger? Did you even get it to reverse? So it looked like, in this case, the wallaby was facing the other way. Now, what's going on here? When light goes through water, it bends. So the water in the glass is like a convex lens which magnifies things, makes them bigger. And the bending of the light can make the image face the other way. Did you notice when your image was really large that it was made up of dots? So this is actually made up of very, very small dots, so small that my eyes can't see them individually and they blend together to make an image. But you might have seen a picture on your computer perhaps where you could actually see, not the dots on your computer, they're little squares called pixels. And it was a blurry image made up of little squares because they were too big and your eyes could actually tell them apart. Now, what about your finger? Could you see your fingerprint? And could you see your grown-up's fingerprint was different to yours? And did your finger look like it was popped around the other way? Depending upon how far away the glass of water was. So when the light goes through the water, it bends, and that was what made the magnification and the reversing happen. Now our balloons. Did you manage to blow them apart? Let's see if I can. Holding them in front of my face about 5 centimetres apart, and I blow between them. They come together. Try it again. I can't blow them apart. If you're blowing right in the middle, they always come together, and that's why this experiment is called kissing balloons and not blown madly apart balloons. So what's happening? If you blow onto your hand, can you feel that the air you blow out is going fast? So that air, that faster air, when it goes between the balloons, makes the pressure between the balloons drop. So when air is going faster, the pressure is less, and is now less than the pressure on the outside of the balloons. And so it is actually that pressure on the outside of the balloons that pushes them together. So that's a pretty hard thing to understand, but doesn't mean you can't have fun experimenting with it. Okay, and our last one, was raw or boiled. Now, I can't tell by looking which one's raw or boiled while the eggs aren't cracked. I can't tell by smelling. Now, children usually have a better sense of smell than their grown-ups, so maybe they could tell a difference. I can tell a little bit by shaking, especially if you've been shaking for a long time, because the raw egg is getting a bit mushed up inside there from all the shaking and starts to wobble around. So I can actually hear a bit more of a wobble coming from my number 2. So maybe that's the raw one. What about putting it in the water? Sinks to the bottom. I think this might be my boiled one. What about the raw one? Will it float because it has been cooked? No, it sinks to the bottom as well. Now, there is a way to tell that's really easy that I haven't shown you yet. It might be something that you already knew. If you didn't already know it, I doubt you would have guessed what to do. So I'll just dry my eggs off. And the way to tell is to try and spin them. So if I spin this one, oh, it spins really well. If I try and spin this one, it hardly spins at all. So which one then do you think would be the boiled egg? And which one would be the raw egg? Do you think the one that's solid on the inside would spin well, and the one that's full of thick liquid on the inside wouldn't? You'd be right. So my boiled egg is number 1 and my raw egg is number 2. So what I could hear slightly was, in actual fact, my raw egg slightly swishing around inside there. So this egg that's boiled is solid all the way through, and when you spin it on the outside, it will spin really well. The raw egg, which is still mushy in the middle, doesn't like to spin. Now, why didn't we get a difference with our cup? Why didn't the raw egg float? It's because even though this one's raw and this one's boiled and now solid, so this one's still liquid and this one's solid, they still have the same amount of egg inside them because we haven't taken any out. So that means they're both going to sink in the tap water as long as they're not going off, like I explained last week. So, well done all our families. You've now finished the Little Bang Discovery Club on-demand version. Well done to our junior discoverers and also to our lab assistants. I hope you managed to hold back and let the children do the thinking. And now you all know how science works. So science is just a systematic way of answering a question. Think of a question, make up a guess, what you think's happening, come up with a test it, see what the results are, and then you can come to a conclusion based on the evidence. So it doesn't have to be in a laboratory, it can be in your home. You can be doing science all the time, and you probably are doing science all the time. Posing questions, how long is it going to take me to get somewhere today? Oh, work it out. Do a test, yeah, I got there early. Next time I don't have to leave quite so early. So you're really doing science all the time. It's nothing special in laboratories that only really learned people can do. Everyone can do science. And I'm hoping that next time your children ask you why, you're going to say to them, let's find out together. Let's try and find a way to answer that ourselves. So that's something that families can have a lot of fun doing together. You can have lots of fun doing science together, making up experiments, testing things, and trying to find your own evidence-based conclusions. Well done, everybody, and I want the children all to grow up and be scientists.